Welcome to part 1 of the video on the Fundamental Theorem of Calculus. In this video we're going to introduce this fundamental theorem, and our goal is to get the intuitive idea behind this theorem. So let's begin with the graph of a function f of x. Here we have the graph of this function in green. We're going to take a point A on the x-axis and a point x in the x-axis, and we know from the previous lessons that the definite integral of this function from a to x gives us this area. Here we use the dummy variable t because we're already using the variable x here. So we use t to avoid confusion. So now what we're going to do is, for each x in the x-axis, we're going to define a of x as this integral as the area from a to x. That's why we use the letter a, because this will be an area function. For each x, a of x is the area under the curve from a to the point x on the x-axis. So here we're just defining an area function. For example, if we take the point x1, a of x1 will be this area, a of x2 will be this other area, and a of x3 will be this area. So this is just a simple function, just as any other function. So now, what the Fundamental Theorem of Calculus says is that you can take the derivative of this function, and if you do that, you will get f of x. That is, the rate of change of this area function at the point x equals the value of the function f, and that is of this green function here at the point x. There is the rate of change of the area equals the height of this trapezoidal shape here, and this is pretty intuitive, because if this height is bigger, the rate of change will be bigger also. So it is pretty intuitive, and let's try to justify a little more of that intuition with this intuitive proof. We know that by definition the derivative of a at point x equals the limit as delta x approaches 0 of a of x plus delta x minus a of x over delta x. So let's try to identify the difference, this difference that we have in the numerator in the graph. Here we have the point x, and here we have the point x plus delta x, and a of x equals this area from a to x. A of x plus delta x equals this other area from a to x plus delta x. So what is their difference? We have a of x plus delta x, there is this area, minus this other area. So we get the area from x to x plus delta x. There is this area. So this area is the difference that we have in the numerator. So now we're going to make delta x approach 0 because we're taking the limit. So we're going to make delta x smaller and smaller. We'll make it even smaller and even smaller. Now let's take a closer look to this region here. Here I have zoomed into this region, and we see that we have here kind of a trapezoidal shape, but we see that as we make delta x even smaller, we can approximate this shape by the rectangular shape. So the area of this shape will approach the area of a rectangle of base delta x and height f of x, and the area of this rectangle is base times height, that is delta x, that is its base, times f of x, there is its height. So we see that as delta x approaches 0, the difference, we have this difference here in the numerator of the limit that we used to calculate the derivative. This difference approaches this area of a rectangle that equals this product. So this will approach, we know that the numerator approaches this, so the quotient approaches this, and we can cancel the delta x and get that this equals f of x. So that's the intuitive justification of this theorem. So this theorem is really essential in calculus because it gives us the intrinsic relationship between the integral and the derivative, and it allows us to calculate definite integrals because we already know how to calculate derivatives, and we can reduce the problem of calculating definite integrals to the problem of calculating indefinite integrals, and we'll see how to do that in the next videos. So that's all for now. Thank you for watching and see you next time.